Okay, so we are back. All right, so here we go. Let's look at this one. So it says let f be the function defined by 3x squared minus x cubed. What's the absolute minimum of f on the closed interval? Okay, this is important. Why is it important that it's closed? Yeah, it could be at those endpoints. That's the extreme value theorem. We're guaranteed an absolute maximum and an absolute minimum. So this is where that candidate's test would come in handy. Okay, so we're going to need to find those critical points. How do we do that? Yep, we take the derivative and find where it equals to 0. So f prime of x would equal 6x minus 3x squared. We're going to set that equal to 0. If we factor, we can take out a 3x. So that would give me 2 minus x equals 0. So my critical points are going to be 0 and 2. Okay. Now, is 0 in our interval? No, because we went from 1 to 5 over 2. Is 2 in our interval? Yes. Okay. So we're going to do our candidates test, and this means we're going to plug it into the actual function. So we'll plug in 1, we'll plug in 2, and we'll plug in 5 over 2. All right. And let's get those y values. If I plug in 1, 3 times 1 would be 3 minus 1, so I get 2. 2 squared would be 4, that'd be 12, minus 8, 4. Ooh, 5 over 2, I gotta do a little math. All right, so 5 times 25 over 4 minus 1 something over 8. Thanks, I was having a minute. All right, so that's going to give me 75 over 4 minus 125 over 8. And if I do a double that, that's going to give me 150 over 8. So 125 over 8. All right, if we look for just trying to figure out, did I get that right? It'd be 25, yes, it would, because I'm a dork. Math, not important. Do y'all know what that quote's from? Probably not. It's from School of Rock.
I haven't seen it.
Oh, that's one of the favorites in our house. We can quote almost every word. Okay, so that gives me what? A little more than 3 1/8. Yeah. Okay, so what's the absolute minimum? Two. Okay, it's 2. Absolute minimum is 2. Questions? Okay, you with me, Jawak? Okay, let's look at our quote for the day, our affirmation. We must accept finite disappointment, but never lose infinite hope. That's a good one. Mm-hmm.
This day is...
Oh, gotta say that.
When is this day?
The 20th, which also happens to be Inauguration Day. So we'll be off that day. Yep.
It's gonna be a mixed day, yeah.
Okay. Alrighty, y'all. Well, so we have talked about increasing, decreasing. We've talked about maximums and minimums, and now it's time to talk about concavity. We talked about concavity a little bit last year, where slopes were increasing. What does it mean if something's concave up? What does it look like graphically? Yeah, it can hold water. What about if it's concave down? Water would fall out. So we're going to get into the why behind it, the math, the calculus behind why that works. And then we're going to use something called the second derivative test to find extrema. It's nice. It saves you a little bit of time if things set up appropriately where you can use it. So that's what we're going to discuss today. All right. So this is appropriate. How fast does the flu spread? Okay. So it says a single person contracts the influenza virus, and now the flu epidemic is spreading through, oh, that's funny. I just saw that word, Calciopolis. All right. Hardy har har. The number of infected people T days after the initial outbreak can be modeled by, and it gives me this nice function. It tells me that the population of the town is 1,000. What kind of function's that one? Looking at how it's written and at our picture, by remember? Oh, an unusual name.
Give me a hint.
Starts with an L. Close. It does start with LOG.
Log.
Logistic. It's a logistic curve. Yep. That's a logistic curve. We recognize it because that top number is what we call the carrying capacity. It's the maximum amount that the curve can attain, right? Sorry, I can't get words to work. It's been a minute since we've mathed. Okay? So it increases slowly, then quickly, and then levels off. All right? So it has that characteristics. It's used a lot to model population. Okay? All right. Bless you. I didn't know if you were crying there for a minute or sneezing. All right, so I want you to take a second and walk through this investigation with your group. There are 5 questions. I think it'll ask you to use your calculator to do some derivatives and stuff like that. So, all right, take a second or a few minutes and let's work through that, spreading the flu. Because it's gotten
Cow coffee was not survive this. And why did we decide? Well, because the food's very small.
Shut up, bro.
Massive increase.
Not saying that.
Yes, it's right.
iced coffee's so good. It could be subarctic and I'm still gonna drink iced coffee. I like my warm coffee at night right before I go to bed.
Just everybody know the one guy that doesn't have
Who has the super immunity, huh?
It can never actually be.
No, it can't ever actually be 1,000. Somebody's not getting sick. I want to be that guy.
Because the
Yep.
Maybe it's Timmy who's trying to cross the bridge.
Yeah, he finally left the island. Wait, what if the island was Kalmar? They were trying to leave. No, I'm pretty sure it's Oh my god.
Y'all.
Finding the table with the values at the front of the combined parentheses. Okay. This is.
Use your calculator to do those.
oh
Yeah, use your calculator. Use your calculator to do the table.
okay.
I was scared for a second.
Yeah, no, you don't have to do those by hand. Or we'll be here all day.
Oh. I didn't say. Perhaps I didn't say it before I used it. Did that even work? Yeah, look at
Are you still in? You were probably not gonna think of it. Not when it's funny, but yeah.
Oh. It was.
When there's secret people out there.
So
You're a secret beatboxer.
It sounds like it could be a show.
Can I talk? It's supposed to be.
I am not.
I write all the parts. Good job.
Good job.
I just found the trick.
But only the beat.
Oh, you put in your.
I don't know if it works, so find your script, you'll see if it actually works, because I just typed it.
No.
That's the Bible.
Why did you tell me?
That's not a good idea.
Roll.
Did I get that perfectly between the back?
Movie toe.
I'm the best athlete ever. I should be silent.
So what, Marvel?
We'll go to South Carolina for more England.
All right, Flu, Parker, focus.
There's just, almost like, I work with somebody, and she already has a PowerPoint.
Really?
Yeah.
Dang it, boy.
Oh,
So it's one, so now what? Multiply, like this?
Yes.
I feel like I could know the general area of South Sudan.
yeah.
I feel like most people don't know South Sudan, but like, they didn't get there.
Well, like, I don't know where Sudan is.
They didn't get Sudan.
I know where South Sudan is.
Yeah. You know what? You're giving it to us, bro.
And because of that, I
If
know
I'm
Sudan.
given a map of Africa, I could get.
Now you have all of your values right there.
I could not.
Chad, South Africa, and Egypt, and Rwanda, Nigeria, that's all.
I'm really bad at math. I would get
Yeah.
gas. I mean, I could get I can get some.
South.
Maybe that's why I didn't see it.
Neither, I wanted something. No?
All right, let's wrap up in about 2 minutes.
That's something.
No, I put in, I did math, and then, like, I put one for the graph, and it was y1 x. You know, when you like, you see what I'm saying? Wait, for the x thing, you did the first. Okay, does that make sense? That's the same, plug in the first. Yeah.
Cuba. Well, I don't really know the islands. I just well, I don't. No one tell me the islands. I just kind of call it a day. Ethiopia.
Wait, one more time.
After you put the, I just look for a small island. I don't really get it.
Oh, this one.
I'll pick one.
And put that in.
I was so pissed off.
So then after you,
We would be more than 50.
that's where I get it.
Can we get that?
Yeah, I'm only getting my box.
Blot out.
I know after.
I know, right? The area, not.
What's the last one?
I'm not doing it right.
I just don't know. I don't think
I know where the
No, it's positive.
Thank you for your first number, after each.
Did the over Zimbabwe? There's one like big one.
So did you get 3.639?
That'll
that's
be
on the other
the.
one. I have a question for you.
Yes.
If you have, if you put Y1 in something,
Mhm.
then just leave Y1, did it still stay as that?
Mm-hmm.
Oh, it did. Oh.
That's what.
Okay, so as you're working, when you get to where you need to take that second derivative, okay, so I went into y1 and I left that equation, I put the equation in, okay, in y2, I'm going to put the first derivative, all right, so math 8, we're going to put y1, so alpha trace y1, and then we're going to put x in there for all x's, okay? You can leave that in there and quit because when I want to take the second derivative, I need to take the derivative of the first derivative, okay? So on my home screen, math 8, this time I'm going to put y2 in there. And then my x values that I'm interested in, which was, the first one was 3. Okay? So you can put it in y equals and do it that way. All right, to keep you from having to type things over and over and over and over again. All right, so that's a good skill. And then just to recall it, second enter lets you recall what you typed in and you can change the x value at the end. Okay, so just a little calculator tip right there, which is a good one. All right, So let's take a look and talk about kind of what's happening there. As we think about what's happening to the number of people over the 21-day period, what happens? How are they getting infected? Yeah, because it's contagious, right? But how's it changing? Yeah, it speeds up and slowing down. It's increasing across the whole 21 days, right? So it's slow at first, it speeds up, and then it levels off. Why do you think that happens? Yeah, there's only so many people, right? And there's got to be a point where the contagion's spreading super quick, but then we don't have as many people to infect, so it has to slow down, right? Because we've gotten up there to as many as possible. When do you think it's growing the fastest? Yeah, somewhere around 11 or 12, it looks like, right? Because we switch right in here somewhere. So I would say between 11 and 12 days. Okay, now let's think about why that's happening. If we look at these little slopes, these rates of change, right? What's going to happen after those 11 and 12, somewhere in there? What happens to my slopes? They start to decrease, right? Our slopes start to decrease. They increase till they get to a kind of a maximum slope, and then they begin to decrease. So the slopes increase, hit a maximum, and then decrease, right? So there's definitely something happening there, okay? All right, so let's take a look at our table. Let's check our values and see how we did with those. All right, so just learning how to use that calculator, it's going to be helpful for us in the future. I'm just going to write down, they didn't do the 3 decimal places on everything, but I'm just going to write down what they gave me. So 3.64, 11.82, 91.094, so you can check your work. 147.91, 46.74, 34.318, and then 3.446. So that's what we should have gotten for our slopes. And that seems to follow what we said, right? The original slope, okay, it was positive across the board, which goes with what we've said, right? We have an increasing function. Our slopes get steeper, all right? If we notice, all right, we get in there and then all of a sudden it starts to come back down, all right? They start to decrease, all right? When we put our second derivatives in there, we get these values, 2.168, 6.842, 34.555, 12.137, negative 14.44, negative 18.19, negative 2.054. What do you find interesting, or what do you notice about those rates of change? Yeah, they switch from positive to negative, which means what has to happen at some point? It has to pass through zero, right? It had to pass through zero to go from positive to negative. We had to pass through a zero to get there, all right? And so notice we think that that's kind of where that maximum slope or that maximum derivative happened, was between 11 and 12. Could be possible that that's happening where that second derivative was equal to zero. So let's talk about, where is the derivative increasing?
The first derivative.
Yeah, the first derivative, f prime. Yeah, it looks like it's increasing from 3 to 11-ish. Okay, and then where is it decreasing? Yeah, from 11 to 21. Okay, now I want you to look at what's happening to the second derivative during those intervals. Okay, what's true about f double prime between 3 and 11? It's positive. Okay, and what about from 11 to 21? It's negative, all right? Go back and look at your graph, all right? Go back and look in your graph for just a second. What do you notice, all right, about this function? Let me switch to a highlighter. Between up to that 11, what do you notice about it? It is increasing, which is consistent with the derivative being positive. It's concave up, all right? What was true about your second derivative right there? It was positive, okay? What happens when we turn the corner wherever that maximum occurs? It's concave down. And what was true about your second derivative at that point? It was negative, okay? Finally, right? Finally. All right, so that's the big takeaway from all of this, okay? That's the big takeaway. Concavity is based on the sign of that second derivative, okay? So how can we get our answer just by looking at the graph, all right? Well, we are, oh, nope, don't write with a highlighter. We are concave up on that interval, which was where F prime increased and F double prime was greater than 0. Okay, so that's what we're going to look for concavity. All right, we were concave down from 11 to 21 because F prime decreased. All right, and that's what we talked about a little bit in pre-cal. And F double prime was less than 0. Okay, the second derivative was negative. All right. So, yay. All right, we've been waiting for this moment, or Gareth has. Gareth and I have been waiting for this moment. Okay. To talk about concavity and how it's related to our derivatives. Okay, so let's just kind of organize these thoughts really quickly. All right, when we talk about things being concave up, we already said, all right, visually, f of x looks like it holds water. Okay. We know that the second derivative is going to be positive. And if the second derivative is positive, that tells me something about the first derivative. The first derivative happens to be increasing. Okay, so visually we know what the function looks like. Right? If we know the second derivative is positive, we know it has to be concave up. Or if we know the first derivative is increasing, then it has to be concave up. All right? So depending on which thing I have, it tells me about the other two. All right? Which is nice. All right? Likewise, if something is concave down, we know visually it's going to spill water, the original function. We know the second derivative is negative, and that f prime is decreasing. And that's important. Right? So now, one piece of information actually tells me a lot. Right? And it just depends on which piece that I have. That's our basic definition understanding of concavity. That's good. All right. So let's talk about how we justify. All right, we know free responses come in. We know they're going to ask us to explain our thinking. What are they looking for in terms of a justification? All right, it really depends on what they give you. Okay, it's going to depend on what they give you. So let's say that we're looking at something graphically, all right? If it's the original function, all right, we can just say by looking at it that it's concave up or concave down, okay? If it's a derivative graph, a first derivative graph, we would have to say it's increasing or decreasing. If it's a second derivative graph, we would have to say if it was positive or negative. So it all depends on what we're given, okay? So graphically, all right, if it's f of x, we can just state what it's doing. If it's f prime, we have to state whether it is increasing or decreasing. If it's f double prime that we have graphically, then we have to talk about is it positive or negative. Okay, and that's how you'll justify. All right, because f prime of x is increasing, f of x is concave up. All right, because f double prime is negative, f of x is concave down. Right, so we have to speak based on what we're given graphically. All right, that's very important. Y'all know how they like to give you graphs and tables and all the things, okay? So we'll use all of that. If we're doing it symbolically, all right, meaning I've just got an equation and I don't have a calculator, all right? Here's what we're going to do, all right? Symbolically, we're going to find the second derivative, all right? We're going to find where it equals 0. Okay, now, I refer to those as hypercritical points, but that's not a real word, okay? So don't use it in writing, all right? We would just say where f double prime equals 0, okay? So that just reminds me of what to do. I have critical points for the first derivative. I call them hypercritical for the second derivative, all right? Just a mental thing for me, all right? And then after we do that, we do a sign chart, all right? If it's positive, we know it's concave up. If it's negative, it's concave down, right? So let's do a couple of examples just to kind of look at all the things it might ask me to do, all right? Question about that so far? Pretty straightforward, but we got to get back in calculus brain. Okay, here we go. So let's look at this one. So it says to determine the concavity of y equals 3 plus sine x on the interval from 0 to 2 pi. Okay. This one's symbolic. They didn't give me a lot of information. All right, so what should my first step be? Yeah, let's take the derivative. How many times? Twice. Okay. So y prime is going to be cosine of x. Y double prime is going to be what? Negative sine of x. We're going to set it equal to 0. Now, think about your unit circle, all right? You're solving a trig equation here from 0 to 2 pi. Where does the sine equal 0? 0 pi, and this time it goes all the way back to 2 pi, okay? So it comes all the way back. So when we think about our sine chart, 0, pi, and 2 pi, right? So we're going to plug everything into y double prime because that's going to tell me about concavity, right? Which is what I'm looking for. So what's a good value that's between 0 and pi? Pi over 2. I would use that one. Okay, pi over 2. All right, and we're going to evaluate it. The opposite of the sine at pi over 2. What would it give me? Negative 1, so I'm going to be negative. If my second derivative is negative, what's true about my function? Concave down. Okay, and then a good value between pi and 2 pi. 3 pi over 2. Okay, so the opposite of the sine at 3 pi over 2, positive 1. So my original function is going to be concave up. Okay, So if we state our answer, all right, y is, I'm going to abbreviate, concave up on pi 2 pi because y double prime is greater than 0 or is positive. And then y is concave down on 0 to 2 or 0 to pi because y double prime is less than 0. All right, so that's where our justification falls. Question about that. Symbolically, typically is the easiest. Well, I don't want to say that. Okay, just depends. Just the work is different for something that we're going to do symbolically. Okay, all right, so now look at this one. This is one that's part of a free response question. Okay, this is where you have to really pay attention to what you've been given. Okay, so the figure above shows, well, actually it's below, the graph of f prime, the derivative of a twice differentiable function. Why is that important? Yeah, I have to know I can take a derivative so I can talk about the concavity. Okay, on the interval from -3 to 4, the graph of f prime has horizontal tangents at -1, 1, and 3. Okay. On what open intervals contained between -3 and 4 is the graph of f both concave down and decreasing? Okay, so we're looking for where is it concave down and decreasing. Let's think about what this derivative is going to have to show me. Okay, so in order for it to be concave down, right, what's going to have to be true about my first derivative? The slopes must be decreasing, okay? And that's a little bit more difficult to look at, all right? The slopes must be decreasing, okay? So take a look. Where does it look like the slopes are decreasing?
So when you say substitute, does that mean like getting more negative?
If they get more negative, that would be decreasing.
Okay, and
Less positive.
Less positive. So this one's a little bit tougher. Okay, so where do you think it's concave down? Let's just look at it for a second. Okay, so let's look. All right, so if we're thinking about where are these slopes getting either more negative or less positive. Okay, so let's look right here. What's happening here? They're getting more negative, right? But they go towards what? They go towards 0, okay? what happens here? My slopes are increasing and they stop at 0.
Are you writing?
Am I writing?
Yeah, it's on.
No, I'm not writing. And then if we go from 1 to 3, they go to 0. And then from 3 to 4, they increase. So what can we mark off for sure that are increasing slopes? Yeah, -1 to 0. Okay. And then what else? 3 to 4. Okay, those slopes continue to increase. Okay, anywhere else? It's getting less negative from maybe like from right here somewhere, 2 to 3 maybe. Okay, and then anywhere else? Yeah. Okay, -2 to -1, I would agree. Okay, I really think that's where the slopes are increasing. Okay, now let's look at the other places. All right, this should be where we are concave down. All right, this slope is getting more negative, and then all of a sudden it starts to shift. All right, this slope is getting closer to 0, so it's decreasing. Here it goes from 0 to negative, so it's decreasing. So we're concave down, it looks like, from -3 to -2 and from 0 to 2. Okay, so that's where we're concave down. Right? Now, let's talk about the decreasing part of the function. In order for a function to be decreasing, what has to be true about the derivative? It has to be negative. Okay, so it's underneath the x-axis. So let's highlight those places. Where is this picture underneath the x-axis? Yep. -2 to 1, to 1, and then 1 to 4. Okay, so we are decreasing -2 to 1, and then 1 to 4, right? So what we're looking for are the places where this is going to overlap, okay? What do you think? Mm-hmm. Okay, so they're going to overlap 0 to 1 and 1 to 2. Okay. Now, reasons. Okay. F of x is concave down and decreasing on 0, 1 and 1, 2 because, okay, f prime of x is decreasing and f prime of x is negative. Right, so that's our reasoning. Yes. Did I have a brain fart?
It's concave down on the -3.
Yep, you're right.
You want the slope to be negative.
Yep, you're right, which is the graph itself, right? Okay. This is why we write in pencil. Okay.
It's negative on -3
Yeah, you're right.
Negative on negative 2 to 1.
Yeah, you're right.
1 to 3.
You're right. Sorry, erase. Ugh. That was me. It's not the slope, it's the actual function. Thanks, Gareth. Next time, don't let me talk so long.
Oh, wait, are we done? Wait, are we like, was it
Like,
starting?
maybe she knows something you don't.
No, I did it wrong. Ugh. Okay, remix. Sorry.
Okay.
It happens. Okay, we're gonna get it right. You probably did it right, and I did it
I wrote
wrong.
it down right, but I kept changing my.
Sorry. Gosh, darn it. Okay. All right. Golly, I hate it when I have a brain sparkle. All right. Back up, punt, get a fresh drink of water. Okay. Here we go. All right. This is F prime. Okay? Everybody with me? Okay. So if we're looking for where the original graph is concave down, I just need to know where is my F prime graph increasing and decreasing. Okay. So let's look at it. God bless it. All right. So if we look at this picture for increasing and decreasing, all right, what's it do first? It decreases, then it does what? It increases, and then it decreases, and then it increases again. Okay? So that's telling me, sorry, I messed that totally up. So I'm going to be concave down everywhere that this picture's decreasing, which is going to be -3 to -1, and then 1 to 3. Okay. That was a whole lot easier than what I was trying to do. Okay? All right. Then the original function is going to be decreasing. Okay, so f of x is concave down, and f of x decreases where f prime is negative, where it's below the axis. So we are below the axis from -2 to 1, and then 1 to 4. Okay. Okay, much better. Okay. Am I doing better, Gareth? Thanks. Golly, it's been a day. All right. This does not bode well for next block. That's all I'm going to say. Okay. All right. So as we're looking, let's talk about where things are going to overlap between those two. Okay? Because I want both things to be true. All right. I'm concave down from -3 to -1. I'm decreasing from -2 to +1. So that overlaps from -2 to -1. Do you agree? Okay. So I'm looking for where these two sets of information overlap each other. Okay. So in the first one, -3 to -1, -2 to +1. So the first place that it's going to overlap is from -2 to -1. Do we agree with that first interval? Okay. So we are concave down and decreasing f of x. So let's switch one. All right. On -2, -1. And then we pick up 1 to 4, 1 to 3. So I'd have to choose. Where do they overlap, those last two? 1 to 3. There we go. Because f prime of x is decreasing and f prime of x is less than 0. Sorry about that. I made that harder than it needed to be. Sorry. We'll do a lot of these with pictures, okay? So we'll get better at them, me included. Okay. Room for everybody. All right. Take a look at this next one. I think you can do this one without me. All right. This one's symbolic. All right. So see if you can find all the values where it's concave down. I don't know if you had bigger pieces of paper, you could actually see it. You feeling good with the micro notes over there? Okay. Everything's micro. Economics, notes. Timmy's micro. Bless. Timmy's getting a bad rap. What'd you do first? All right, so let's get the first derivative, 3x squared minus 12x. Then let's get the second derivative, 6x minus 12. We'll set it equal to 0. So that's going to happen at x equals 2. Okay? Now, what is the domain of this graph? It's all real numbers. It's a cubic, so it's all real numbers. So when we do our sign chart, 2 is the only number that's going to be on it. Okay? We're going to plug it into the second derivative, and it's going to tell me about the function. Okay? So if I plug in something less than 2, what would be a good one? 1 or even 0. All right? If I plug it into the second derivative, 6 times 0 minus 12, that's going to give me a negative. That means my function is concave down. Something bigger than 2, probably pick 3. 18 minus 12 would be positive. So we are concave up. So we just have to justify where is it concave down. We would say h of x is concave down on negative infinity to positive 2. Why is that? Because h double prime is less than 0. Right, so that's your justification statement. What?
I didn't charge my iPad last.
For shame. We'll charge it before you get to Miss Edwards' class so you don't have to pay for a battery bank or whatever it is y'all have to do. This is why y'all charge them in here, isn't it? It's exactly why. Okay, it's all right. I'm learning. She's slow, but she's got cute shoes. Okay, here we go. Okay? All right. So, what do you think? We know that 2 is important, all right? What's happening right there at 2? We're switching concavity. Obviously, that needs a name, okay? So, this is what we call it. We call it a point of inflection, okay? A point of inflection. It is an ordered pair. Okay, it's an ordered pair. It is the point on f of x, all right, where f double prime at x is equal to 0 and changes concavity. So it is the point on f of x where f double prime is equal to 0 and where we change concavity. Have you been assigned a role yet, Parker?
No.
Are y'all reading?
Which,
Are y'all reading today?
yes, and then we should be getting our roles in the next few days.
Okay.
For Alta County Theater,
No.
Robin Hood.
It's our next play.
do y'all do something?
Alternate theater is more of a retreat. We will probably do a small play at the end, but it's more or less working on techniques and stuff. Yeah, but I think I get to be out of school all day.
You do?
So I'm just excited for that.
Yes. All right, so let's talk about how we justify a point of inflection. All right, symbolically is the easiest. It is where the second derivative changes sign. Okay. So a point of inflection, it's where our second derivative is going to change sign. And it has to equal 0. Okay. Now, It really depends graphically on what they give me. All right, what they give me. If they give me the first derivative graph, okay, it's where f prime of x changes from increasing to decreasing and has a horizontal tangent. Okay, why would that horizontal tangent piece be important? Yeah, because the slope would equal what? 0. And that's what we're talking about, okay? The slope would equal 0. And then if they gave me the second derivative, all right, changes from positive to negative. Or vice versa. Okay.
I watched it this morning and it's not dried yet, so I don't know if it looks like super just wet still. Is that good?
I don't think it looks greasy.
It looks fine. Okay. I don't think it dries anything. It's kinda cold.
Do you ever blow dry your hair? You always air dry it.
I don't have a blow dryer.
Oh, okay. So the second. Okay.
That's really cool. I'll still have mom.
Yeah.
It takes so long to.
Yeah, I would think it takes a long time to blow dry your hair. All right, let's look at this one. Okay. So it says to find all the points of inflection for this graph, y equals e to the negative x squared. Okay, do y'all know anything about that graph? No, me neither. Okay, I don't. So we're going to have to go about it symbolically, which is going to make it a pretty interesting thing that's about to happen. There's going to be a lot of algebra in here. Okay, so because we're discussing a point of inflection, we've got to start with the second derivative. Okay, which means first derivative first. All right, e to the negative x squared, what's going to be the derivative? E to the negative x squared, is that it? No. It's chain rule, so derivative of negative x squared would be negative 2x. Okay, so that's y prime. Y double prime is going to get even more interesting. All right, because what I have here is a product rule. Okay. I wish y'all could see Gareth's face. Okay, so let's do the product rule. I'm pretty sure I lost your complete eyeballs there for a second. All right, so here we go. First, times derivative of the second plus second times derivative of the first. Okay, it got nasty real fast. Okay, because you had to use that chain rule again. So that's going to give me negative 2 e to the negative x squared plus 4x squared e to the negative x squared. All right, and now I got to set that bad boy equal to 0. All right, say it ain't so, Joe. Okay, so it would help me if I could factor. All right. Is there anything that's common to both?
Probably a 2 e to the negative x.
All right. An e to the negative x squared for sure. And a 2. I agree. Okay. Let's pull out a 2 e to the negative x squared. When I do that, that's going to leave me with a negative 1 plus 2x squared. Okay. All right. Okay. Okay. Life's not terrible. Now, we've got to set both of those equal to 0 to solve for x. Okay, question. Is e to the negative x squared going to equal 0? No. Okay, so I don't really care about that first factor because it's never going to equal 0. And e to the x function never hits 0 anyway. Okay, so I don't have to worry about it. If I look at the second piece, that's going to give me 2x squared equals 1, or x squared equals 1/2, or x equals plus or minus the square root of 1/2. Okay, or 1 over the square root of 2, however you want to think about it. Okay. So when we go to our sign chart, all right, things are going to get pretty interesting because I've got to put a negative square root of 1/2. Whoops, can't write. And a positive square root of 1/2. Why are hiccups funny? But they are. They're not funny to the person hiccuping, but okay. Give me a number in between.
0.
Woo! Praise the Lord. All right, 0. Okay, we put 0 in there. Now, if I choose 0 in the middle, I'm plugging this into this nasty second derivative down here that I've factored. Okay, 2e to the negative 0 squared. Is that going to give me a positive or a negative number? Positive. Negative 1 plus 2 times 0 squared. That's going to give me a negative. So positive times a negative is a negative. All right. Now, let's think about a value that could be bigger than the square root of 1/2. 1. Okay. I mean, I'm going to use something easy. All right. You could even use 2. All right. It doesn't matter. Okay. So if we use 1, all right, 2 times e to the negative 1, doesn't matter. It's 2 over e. Is it positive or negative? It's positive. Okay. 2 times 1 squared is 2. All right. Plus a negative 1. It is positive. Positive times a positive is a. All right. So we're going to be concave up. Now, is that going to change when I pop in a negative 1? No, why not? We squared the x. All right, we squared the x everywhere. So it too is going to be positive. Okay. All right. Points of inflection. And this is where it gets interesting. I said pot. Nope. Nope. How many points of inflection do we have? We have 2. They happen when x is negative square root of 1/2 and when x is positive square root of 1/2. Okay, now this time it has to go back into the original function. All right. All right, don't panic. If I plug it back into the original function, because I want the coordinate on the function, all right, if I square the square root of 1/2, what am I going to get? Thank you. Okay, I'm going to get 1/2. All right, so I'm going to get e to the negative 1/2. And what am I going to get the next one? E to the negative 1/2. Okay. Bada bing, bada boom. Okay. What do you think? Wish we weren't. Okay. It's all right. Yeah.
Like, we just, like,
Okay. I'm going to skip the next example just for the sake of time because I want to get to some other things. Okay. All right. Let's look at this one. Because I think this one's interesting. Okay. All right, I think this was interesting. It says use y double prime to explain why the graph of y equals x squared plus cosine x cannot look like the graph at the left. All right. Okay. So if they want me to use y double prime, what do you think might be a good thing to do? Find y double prime. All right. If you don't know anything else, we could at least do that. We'd probably get some points for that. Okay. So let's find y double prime. Okay. Are there some definite points of inflection in this graph that they showed me? Yes, concavity changed a lot. Okay, so there are some definite points of inflection. So let's see if we can find any of them. Okay, if I start to solve the second derivative equal to 0, so negative cosine of x equals -2, or cosine of x equals +2, are there any values where cosine equals 2? No. Okay, it's beyond the domain of the cosine function. So are there any points of inflection for y equal x squared plus cosine of x? No. Okay, there are no points of inflection. Okay, so y, okay, is concave up for its entire domain. Okay, because y double prime is always positive. Okay, how do we know it would always be positive? Yeah, cosine can't be equal to 2, so it's got to be somewhere between -1 and 1, right? And if I do that, 2 minus a -1 would be 3. 2 minus a +1 would be 1, right? So it's going to always be positive. All right, and that's your justification. Another thing you could say is that y has no points of inflection, okay? Because y double prime never equals 0 for any x value. All right, so you could use both of those explanations.
How do you know that it's always positive?
Because the cosine function itself, if we think about cosine, this piece, it goes between -1 and 1. And if I plug that in, 2 minus a -1 would give me a +3. If I just think the maximums.
Oh, okay.
Okay, and then 2 minus a -1 would give me 1. So it's going to stay positive. Okay? All right, and then let me double check just a couple things. Yeah, we might not finish. It's okay. All right, let's look at this next one. This is a good one. Okay. So it says the graph of the derivative of function f on the interval -4 to 4 is shown below. So this is the f function. Answer the following questions, justify your results with information obtained from the graph of f prime. Oh, just kidding. This is f prime. Okay. So this is my f prime graph. So let me write that down so I don't forget. Okay. So it wants to know where is the function increasing, and they gave me f prime. So what would I be looking for? Where it's positive. Okay, so I'm looking for where f prime is positive. Okay, so let's list those. Where's it going to be positive? -2 to 1. Good. Okay. So where is f prime positive? -4 to -2 and -2 to 1. Where is it concave up? What are we going to look for there? Where f prime is increasing. So where is this graph increasing? Follow the function. What's it doing first? Decreases, then it increases. -2 to 0. Then it decreases. And then 3 to 4. Okay. Now, this one's good. Okay, this one's good. At which x coordinates does f have local extrema? Okay, how do we know when we have extrema? It's the 0 of f prime. Okay, so that's important. So f prime is going to equal 0 All right, so where does that happen? My only options. -2, 1, and 4. Okay. Now, is this a closed interval? Oh, it's asking for local, so it doesn't matter. Okay. So now let's look at what else are we looking for? Not inflection points for extrema. Think about your sign chart. When we were thinking about minimums and maximums, what were we looking for? Where we changed from positive to negative. Okay, so maximums were positive to negative. So local max. Okay, local max. Where did I change from positive to negative? At 1. Okay, so I'm going to have a local max, all right, at x equals 1. All right. Now, this is a closed interval, so do we have to think about the endpoints? Yeah, we do. Okay. Now, we're not going to know if these are the absolutes, all right, because I don't have enough information, but I can think about what would happen. So I have my endpoint, and then my function is my derivative is positive, which means my function's doing what? Increasing. So if I have an endpoint and I increase after it, what's that endpoint going to be? A minimum. Okay, because it's going to be lower than what comes after it. Does that make sense? Because it increases after that endpoint. So I'm going to have a local min at x equals -4. All right. Then we're going to go over to the other endpoint. Okay. Going up to the x equal to 4, the derivative is negative, which means my function's doing what? It's coming down to that endpoint. Okay. So if it's coming down to that endpoint, what's true about that endpoint? It's a minimum. Okay. And that's interesting. Okay, that's it. You got to think about those endpoints. You got to physically think about what the graph looks like because we're looking at the derivative. Okay. Now, the last thing it says is what are the x coordinates of all points of inflection? In other words, where did we change concavity? What were the zeros or the horizontal tangents? Okay, the horizontal tangents of the function of the derivative. Where did they happen? We've got one at -2. We're going to have one at 0. And at 3. So the horizontal tangents. Okay. Now, last one, best one. All right. It says to sketch a possible graph of f. Okay. And this is where we've got to put everything that we've just talked about together. We know it's going to go from -4 to +4. All right. We don't know where we start. Okay. So just for my sanity, I'm going to start right here. All right. We know there's a min at 4. All right. And then it's going to increase up to -2. Okay. It's going to increase up to -2. Is it going to be concave up or concave down? It's going to be concave down. So it's going to increase and be concave down. All right, till I get there, and I'm just going to put a dot so I know that I've dealt with it. Okay, because it tells me I have a point of inflection at -2. So I've got to switch my concavity until I get to 0. Okay. Are we still increasing from -2 to 0? Yeah, because we're above the axis. So we're going to be concave up till I get right there. Okay. Then it tells me I'm going to switch concavity again. All right, so I switch concavity at 0. And then I am above the axis. All right, so I'm going to be concave up. But my function is going to do what? It's going to decrease. Okay, so we're going to be concave down and decrease until I get to where? I should have gone over one more. Actually, I've got 5 on here. All right, and then the last piece. All right, so I'm going to switch concavity at 3. So I'm going to go back concave up from 3 to 4. And 4 is going to be a minimum. It's below the axis, so we're going to decrease. Possible graph. Not perfect, but possible. Yep.
Not possible, you increase until 1, and you have to
Oh, dang it.
and then you go down.
God bless it, Gareth. I gotta increase to 1. Yeah, I gotta keep increasing to 1. Thank you. And then a turn, don't I? All right, there we go. All right, so just learning to read the graph. Okay, here's what I'm gonna do. All right, because it's time to go anyway. All right, we're gonna finish this up tomorrow. All right, give us some time to practice. Since I've made a mess today, we're gonna need to practice tomorrow, so maybe we can all do better. Okay, fair enough. All right, there you go. No wrap up. We'll do all of that tomorrow. Okay, grab your